So let's do some concatenative sound synthesis with AudioGuide. For this example, I'm going to use the following sound as my target. And the first corpus collection I'm going to use for concatenation is a 10-minute long sound file from the BBC Sound File Library that is a collection of birdsong. Here's how this concatenation sounds with the target and the birdsong corpus. I'm going to switch out that corpus and instead use a folder of speech recordings of vowels and consonants with the same target. Here's a different corpus. This is about 50 percussion sound files I downloaded from Freesounds. This is a much longer corpus now. It's again a somewhat percussive collection of sounds, but this one's a bit glitchier and has a huge number of sounds that are included. In the case of this particular corpus folder I'm using, it's got 22,000 different sounds that AudioGuide is searching through to try to recreate the temporality of the beatboxing target. I'll comment out the line of the code so you don't hear the target sound file, but only the corpus. There's another corpus collection. This one's simply some staccato notes on the violin from the Vienna sound file database. And finally, here's a recording of individual notes on the piano concatenated with the beatboxing target. In this next example, I'll be showing you a little bit about the controls that AudioGuide gives you over density in the concatenative process. Here I'll be using a target sound file, which is about a 10-second long recording of speech.
That I don't think I'll be able to get all 90 stories written.
And for the corpus, I'll be using the same resource that I used in the very last example. And that is a folder of sounds, each of which is an individual note on the piano. I've got notes at different dynamics and at different pitches. So that's my corpus resource. For this first concatenation, I'm just going to make it so that for each fragment of speech, AudioGuide picks one piano sound.
But I don't think I'll be able to get all 90 stories written.
For the second example, I'm going to let AudioGuide pick a 4-note vertically aligned chord for each fragment of speech.
But I don't think I'll be able to get all 90 stories written.
Next, I'll let AudioGuide pick up to 10 piano notes for each fragment of speech, but they don't necessarily have to be vertically aligned and can happen at any moment during each speech fragment.
But I don't think I'll be able to get all 90 stories written.
Next, I'll let AudioGuide pick a stream of piano notes. And for this final example, I'll let AudioGuide pick a lot of piano sounds to match the speech target sound we have. And AudioGuide is going to pick, in some cases, hundreds of piano samples for every fragment of speech it finds in the target. So let's stick with our speech as our target. And here I'm going to do an example which shows you a little bit more about how AudioGuide layers sounds from the corpus to approximate the temporality of the target sound. So I'm going to run this options file now in AudioGuide. We're going to be using, like I said, speech for the target.
The lecture is so soon.
And for the corpus, I'm going to be using a 10-minute long sound file, which consists of different sounds made on a snare drum. Quite a wide variety of different things in this sound file. Different sticks, different implements, different ways of playing the drum. And I'm going to tell AudioGuide it can select up to 12 elements of this snare drum recording to approximate each segment of speech. And instead of using the default C sound output renderer, which is what plays the sound at the end of concatenation, I'm asking AudioGuide to create an AAF file. You can open AAF files in both Logic as well as Pro Tools. Here's the file that AudioGuide just created. I'm going to open it in Logic now. And you will see here both the target sound file.
The lecture is so soon.
As well as all of the selections that come from the snare drum, 10-minute long snare drum recording, which you can see overlap pretty densely at certain moments. I can, of course, play everything at the same time in Logic.
The lecture is so soon that I don't think I'll be able to get all 90 stories written.
Now you can see here a sort of visual representation of how sounds are layered on top of each other from the corpus of sounds to approximate single segments of the speech. I want to just focus in on one passage in particular. Let's loop a portion of this concatenation.
Stories written.
I'm going to mute the target. And now I'm just going to step through the target one voice at a time and gradually add more and more voices to show you the way in which sort of individual elements of this target gradually get more embellished and more temporally interesting through this layering process. So here's the first voice of corpus selections. Second, with the third. AudioGuide gives you a lot of flexibility for matching segments of the corpus to segments of the target. There's many different sound descriptors you can use, and there's different parameters you can pass to AudioGuide, which will tell it how to use descriptor data to evaluate similarity between target and corpus segments. So in this example, I'm going to use a clip of the target we used last time.
All 90 stories written.
And for the corpus, I'm going to use a database of percussive sounds that are both noisy as well as some sounds which are pitched. And for this first concatenation, I am going to match percussive sounds to fragments of speech according to zero crossings. And I'm going to average the zero crossing time varying series for each sound segment in the corpus and the target into a single number.
All 90 stories written.
Here, instead of averaging the zero crossings into a single number, I'm going to take the minimum zero crossing.
All 90 stories written.
Here, I'll take the maximum.
All 90 stories written.
Here we'll match on the standard distribution of zero crossings for each target and corpus segment.
All 90 stories written.
Here we'll match on the skewness of the zero crossing time varying series for each segment.
All 90 stories written.
Stats gives you a combination of minimum, maximum, standard deviation, average, skewness, and kurtosis.
All 90 stories written.
In addition to matching statistics or averaged descriptors, you can also match directly on the time series. If I just write zero cross, I will match the time varying zero crossings from sounds of the corpus and sounds of the target.
All 90 stories written.
By default, this does a relatively simple Euclidean distance, but you can also do things like dynamic time warping.
All 90 stories written.
And in addition to matching on the time varying series, you can also match the first order difference of the time varying series.
All 90 stories written.
And the second order difference of any time varying descriptor.
All 90 stories written.
In addition to giving you lots of different kinds of controls over descriptors and how descriptors are used to match similarity, AudioGuide also lets you create custom search functions to match target and corpus segments. For this example, I'm going to use the following target sound. Which you can hear has a kind of bifurcation between pitch sounds and noise sounds. And to try to match this target, I've designed the following search function, which I'm going to sort of translate for you now. So the search function is evaluated to match each target segment to segments of the corpus. And this search function is going to start by saying, for each target segment, test its average noisiness. If it is above 0.5, you may only pick sounds from the first element of the corpus list. If it's not above 0.5, you can only pick sounds from corpus elements 1, 2, 3, 4, and 5. Then the results of this first pass are passed on to the second search element, which evaluates the samples that are left according to averaged MFCCs to find the best match. As you can imagine, the way I've divided up my corpus is that the first element is noisy, the last 4 elements of the corpus are pitched, and so in this way I'm trying to model the noise and pitch bifurcation of the target with my search structure. This is the target again. And here's a concatenation with that search structure in AudioGuide. For this next example, I'm going to use a fairly complicated target in the sense that it's got multiple streams of content. It's polyphonic. It's from a percussion piece by Brian Fernyhough called Bon Alphabet. And I'm going to match that sound file with a folder of woodblock sounds. Single dynamic woodblock samples, super straightforward, using Centroid. And if I just run this concatenation as it is, we get some okay results. But as you can hear, the output isn't copying the polyphonic aspect of the target sound file, because essentially descriptor analysis and concatenative synthesis more broadly is, in a standard sense, monophonic. So here's just the woodblock output. And I'm actually going to visualize the concatenation we just made in MaxMSP, loading AudioGuide's block roll output file into Max. It's a patch that comes with AudioGuide. It visualizes the target and all the corpus selections. So to try to work more effectively with polyphonic sound file resources, where there are multiple percussion instruments that are happening in each of these different segments that AudioGuide has found, AudioGuide lets you use signal decomposition on the target to split it into multiple streams of data. You do this using the decompose keyword, specifying the number of streams, specifying how decomposition happens, in this case, non-negative matrix factorization. And when I run this code, AudioGuide is going to create a new target file automatically that is the original target's audio split into 5 different streams that are set alongside each other in time. So here's the first stream, second stream, third stream, like this is the last stream. But it doesn't sound amazing, but what AudioGuide is going to do is it's going to use this temporary target sound file to do descriptor analysis and concatenative synthesis, and then fold all the selections back into the original temporality of the target so that effectively we're doing polyphonic matching with signal decomposition. So here's, I'll run the script, you'll hear the output in the woodblock format, and then we'll take a look at the output in Max. Again, here's the original. And here's our new output in the Bach roll format. You can see now our target is represented polyphonically. And likewise, the corpus represents those polyphonic selections now. AudioGuide's Max MSP interface with the Bach package was created in part so that you can use AudioGuide to create acoustic scores. So here I've got an example file with the same target that we've used multiple times of speech.
The lecture is so soon.
And for my corpus, you can see I've got a much larger collection of sounds than I've had before in this example video. I've got sounds from the violin, sounds from the viola, and sounds from the cello. They're all separated. They're all put into different folders according to playing technique. And for each of these sounds, I give AudioGuide some information about articulation. I make the violin staccato notes staccato. I make the pizzicato notes have the annotation pizz, as well as give them an X note head. In addition to giving some information about notation in each of these corpus entries, I also tag them with an instrument name. Then, in this second part of the options file, I create my instruments. Here I define any number of instruments I want that use those sound resources and some information about how they can behave in time. First, let's run this example.
The lecture is so soon that I don't think I'll be able to get all 90 stories written.
So let's open the output of this concatenation in our patch that comes with the distribution that uses the Bach roll object. You can see here I've got all 4 instruments that I asked for in my options file, and I've got for each instrument selections which are reasonably playable, which is to say you can set restrictions about how fast notes can be played in succession. You can set restrictions about polyphony. You can set restrictions about how quickly they can change from one kind of sound technique to another. So you can see in the violin part, for instance, I've got a restriction on how fast you can move between pizzicato and arco, and that's respected in the output concatenation. Let's just listen to violin 1. So you can play back all of these different elements in Bach and Max MSP, but the, of course, really interesting thing about Bach is that not only can you manipulate and listen to and explore this data, you can also, of course, quantize it and make proper musical scores for instrumentalists.